When we looked at binary trees before, we acknowledged that they can get very good performance if they're balanced, but that balancing is a challenging task. Now it's time to take that on a little bit. So our main goal, if you think back to it, is to implement a search operation that does better than O of n, but doesn't take additional costs to insert or delete. If we, for instance, insert into a sorted array, that's going to be potentially O of n to shift everything over. And if we use something like a linked list that's cheaper to insert or delete from, then we won't be able to get O of n performance. We go with a binary search tree, but we need one that is easy to insert and delete, but keeps that nice branching factor, that nice balance to it. So we will look at this idea again that the search actually takes O of h time in a tree, and the problem is that h could range from what we want it to, log n, to what we definitely don't want it to be, n. If our tree has no branching to it and is just essentially a twisty linked list like this one, versus the tree that we'd like to have, where everything is nicely spread out and the deepest that you can go before you hit a leaf is log n. We know that balancing our trees would improve search performance, and it would be great to have perfect balance, like the tree we saw a moment ago, where it's completely even on both sides of any given node. Or at the very least, if we can't have that because there aren't the right number of nodes to fill it all out, then we could get only having gaps at leaves. We may settle for pretty good balance, where we allow a little bit of imbalance, and that's going to be part of the design of an AVL tree. The AVL stands for the names of the people who designed it. By the way, don't try to figure out how it might relate to the behavior of the tree. We will adjust when we actually use the data structure for another design called splay trees. And we may also allow multi-way search trees where we allow the number of children to be more than 2. But for this time period, we're going to focus on AVL trees where we'll try to attain about perfect balance. Looking first at what a perfectly balanced tree could be, ideally, it's one in which every level is completely filled. We won't always have the right number of nodes to completely fill the tree. For example, if you have 2 nodes, you can have a root and 1 child. You cannot have a perfectly balanced tree because there can be no other child to balance the 1 child out. So we'll consider that to still be a perfectly balanced tree for the size that it is. If it had 3 nodes, we would expect it to be a root and 2 children. One such tree is called a complete tree, where every level is full. That's the perfect one that we want, where we can completely fill out the leaves, and all leaves at the last level are as far to the left as they possibly can be, again, giving us that full tree. Maintaining perfect balance, though, can be expensive. So, for example, this is a complete tree that's created here at the end, where we have all of the nodes and all of the branches being completely filled out. That can be very expensive to readjust everything to try to make it completely balanced like that. What AVL trees will do is to use a balance factor by ensuring that the height of the left and right children of every node differ by no more than 1. So we won't be perfectly balanced, but we won't get very deep branches that aren't very wide, like we saw in that one example where it was essentially a list. The height of a node is the longest path from that node to a leaf. So in this tree here, the height is labeled. If you are a leaf, your height is 0. If you are the parent of a leaf, your height is 1. And in this case, the root, which is the parent of a leaf, is 2. Each AVL node stores its own height so that we can track that and do adjustments if they're needed. Here we are. AVL stands for Adelson, Velsky, and Landis, its creators. So to calculate the height, we find the max of the height of the two children, and then we add 1 because we're one level above them. Each AVL node stores its height. The balance factor of a node is the height of the left subtree minus the height of the right subtree, which is not precisely the balance all of the time, but it should get us close. So if we take the left height minus the right height, the order on whether we do left or right is really unimportant as long as we're consistent within the same tree. If somewhere you switch and you do right minus left, then your negatives will be positive and your positives will be negative, and it would get your data structure very confused. But as long as you're consistent in whichever choice you go with, it should be fine. We will stick with left minus right. So if we're asking questions on assignments or tests, you'll want to remember left minus right. If a particular child node is empty, is null, then we'll consider that to be a height of -1 so that we can use that as a base case to calculate the parent's height as 0 and the parent of that one's height as 1, and so on. We will allow the balance factor to only be -1, 0, or 1. It's not perfect balance, but it's pretty good balance. And in the incomplete trees, we know that some nodes would have a balance of -1, 0, or 1 anyway. So the balance factor, again, is the height of the left minus the height of the right. And we go back through that tree, and you can see that math executing there. 0 minus 0 is 0. So that's the balance factor of this node with 4. And then we add 1 because it's a parent, and its balance factor is now 1. Or its height is now 1, rather. And we can do that for all of the nodes throughout here. In this one, we've got the 8 added to it, and so 9's balance factor changes to 1. I'm sorry, its height changes to 1 and its balance factor changes to 1 because 0 minus -1 is 1. And then the root does not change because the balance here is still the same. The balance factor of the root does change though because it's 1 minus 1 equals 0 now. Each side has 1, but its height is still the same. And we want those small height values. So the height of an AVL tree with n nodes is less than 1.44 log 2 of n plus 2. Therefore, AVL find operations will be within O of log n. There's a constant factor times a log n. We're fine. It's not perfect. You can see this example of an AVL tree here. And so as I pointed out, there are ways in which this tree could be redistributed. All these ones that are sort of sinking down here could have probably been redistributed to fit into the leaves somewhere in here. You've got an empty space over here to the furthest left. It's not terrible though. So our goal again with an AVL tree will be to keep these insertions and erases to log n as well, so that our insertions and erases do better than in, for example, a sorted array where we might do binary search. And we will dig more into this soon, but I want to show an example of how an insertion can mess up the balance factor, and we'll start to think about it. So you can see this example here. We're inserting the 7 because it could only go to the left of 8. That's the only place in the binary search tree where it's legally allowed to go. It messes up the height and the balance factor of this tree here. And so what we're going to start to think about, though, is that it's actually not too bad right now for 7 to be on this right subtree from the root. There's a simple procedure that we could follow to shift and to rotate to where if 8 were in the place of 9, this tree would be perfectly balanced. And so we'd like to look at how we can make a tree actually do those kinds of shifts without incurring a huge amount of extra cost.